Assalamu alaikum, meet Ismail, an absolute technology genius.
He'll take you from basic electrical theory straight into real, hands-on builds.
Hit subscribe for weekly explainers and let's start building today.
Hey everyone and welcome! Today we're unpacking the hidden world of a component you probably use, hundreds of times a day without even realizing it. We're talking about capacitors. Now at first glance, they just look like tiny little cylinders sitting quietly on a circuit board. But hey, do not let their size fool you. These ubiquitous little components can pack a truly shocking and sometimes literally explosive punch. But whoa, hold on a second. Before we get too far in, we need to establish the stakes here. Electricity is inherently dangerous, right? And capacitors command real respect. Touching the terminals of a charged capacitor can cause a severe, potentially fatal shot. And yes, that's even when a device is completely unplugged from the wall. And if you push a capacitor past its limits, well, it doesn't just quietly fail, it can literally explode. So, to keep things safe and make sense of all this, here's our roadmap for today's explainer. First, what is a capacitor? Second, the water tank analogy. Third, inside the two plates. Fourth, why we need them. And finally, reading and testing capacitors. All right, let's jump right in with section 1. What is a capacitor? The fast battery. What's really fascinating here is the perfect contrast between a capacitor and something we're all super familiar with, the standard battery. So both store electric charge, sure, but they do it in completely different ways. Think of a battery like a marathon runner. It stores this massive amount of energy, but it releases that energy relatively slowly over a long period. A capacitor, on the other hand, it's a sprinter. It stores significantly less overall energy than a battery, but its absolute superpower is speed. It can charge up and dump its entire payload of energy almost instantly. And that rapid-fire capability, that's exactly why they're absolutely essential on almost every circuit board ever made. Moving right along to section 2, the water tank analogy, smoothing the flow. To truly wrap our heads around this rapid energy release, it really helps to ground the invisible mechanics of electricity into a physical visualization. Picture a pipe with water flowing through it. If you shut a valve, boom, the water stops instantly, right? But place a water tank just after that valve, and everything changes. When you close that main valve, the main supply stops, but the full tank continues to provide a steady supply of water until it completely empties. Well, in an electrical circuit, a capacitor is exactly like that water tank. If a simple circuit rapidly clicks on and off, a connected light bulb would flicker like crazy. But add a capacitor, that light stays perfectly smooth. Okay, section 3. Inside the two plates, microscopic energy. So let's zoom way in. Inside a basic capacitor, you've got two conductive metal plates, usually made of aluminum. But here's the catch. They aren't actually touching. They are separated by this absolutely crucial physical barrier called a dielectric. Basically, this is an insulating material, something like ceramic. And because it's an insulator, electrons can't just pass straight through it. However, the dielectric has this really special property. It polarizes when it comes into contact with an electric field. And honestly, that polarization is what makes the whole magic trick work. Now, to see what happens next, we can map the concept of voltage directly back to our water metaphor. I know voltage can sound a bit intimidating, but it's simply electrical pressure. Think about it. When you use a pressure gauge on a water pipe, you aren't just measuring a single random point. You are comparing the pressure inside the pipe to the atmospheric pressure outside. Voltage works the exact same way. It is literally the difference in electrical potential between two distinct points. Like, if you measure both ends of a standard AA battery, you read a difference of 1.5 volts. If you measure the exact same end, well, you read 0, because there's no difference. And this brings us to a brilliantly cool phenomenon that we can think of as the Great Electron Standoff. Imagine connecting a capacitor to a battery. The battery's voltage, its electrical pressure, pushes negatively charged electrons onto one of those aluminum plates. Now, remember your basic high school physics, right? Opposites attract. So these negatively charged electrons desperately want to pull toward the positively charged particles on the opposite plate. They are violently attracted to each other. But they are completely held back by that ceramic dielectric insulator. They literally cannot cross the gap. This intense, invisible pull between the two sides creates a stored electric field. The electrons are locked in a standoff, building up electrical pressure, building up voltage, until the capacitor perfectly matches the voltage of the battery. If you disconnect the battery, those electrons, they stay right there, trapped in their standoff, eagerly waiting for a new path to open up so they can finally flow and power your circuit. Which leads us to section 4, why we need them. Real-world uses. So, where do we actually use these things? The short answer is everywhere. Seriously, the sheer scale of their application is staggering. You're going to find tiny surface-mounted capacitors on practically every simple circuit board in your home. We're talking from your TV remote all the way to your laptop motherboard. But they don't stop there. They scale up massively. Huge, heavy-duty capacitors are absolutely critical components in large industrial power systems and even massive skyscrapers. Let's actually look at some specific examples. Right in your own home, things like induction motors, ceiling fans, and those bulky air conditioning units, they rely on relatively large capacitors just to get spinning in the first place. Now scale that up to an industrial level. Large buildings use giant capacitor banks for something called power factor correction. Basically, when a building uses too many heavy inductive loads, the electrical current starts to lag behind the voltage. That makes the whole power system highly inefficient. So capacitors are brought in to counteract this, snapping the current and voltage back into perfect alignment. And here's another huge one. When engineers need to convert alternating current, the AC power coming from your wall, into direct current, or DC, which is what your electronics actually run on, well, doing that creates tiny gaps in the power wave. Capacitors step in, acting exactly like our water tank from earlier, rapidly releasing energy to fill those gaps and perfectly smooth out the power supply. All right, home stretch. Section 5, Reading and Testing Capacitors, your hands-on guide. Say you are holding a standard capacitor. If you look at the side of it, you'll notice a stripe indicating the negative terminal and 2 really vital numbers. The first number tells you its capacitance, basically its storage capacity. This is measured in farads, represented by a capital F. Although in reality, most everyday capacitors are so small, they're measured in microfarads. That uses a symbol that kind of looks like a little U with a tail. The second crucial number you'll see is the electrical pressure limit, and that's measured in volts, marked with a capital V. Now, take close note of that specific voltage number printed on the casing. I cannot stress this enough. This is not a suggestion. It is an absolute maximum rating. If you push the electrical pressure past this exact limit, the dielectric fails. That great electron standoff breaks down violently and, well, you get those slow-motion explosions we warned about at the very beginning of the explainer. And because of all that stored energy, you must follow strict safety protocols when handling them. So if you want to check a capacitor with a multimeter, first switch your meter to read DC voltage. Connect the red wire to the positive side and the black wire to the negative side. Now, if your meter reads several volts or more, stop immediately. Seriously, do not touch those terminals with your bare hands. You have to safely discharge that stored energy first by connecting the terminals to a resistor, letting all that pent-up energy bleed off harmlessly. You just continue to monitor the voltage until it drops safely down into the tiny millivolts range. Only then, and I mean only then, is it actually safe to handle. Okay, so once it's safely discharged, you can actually test if the capacitor is healthy. By switching your multimeter over to the capacitance function, assuming your model has one, you can measure its actual real-world storage capacity. And what's super fascinating here is seeing the difference between theory and reality. For instance, if a capacitor has a stated ladle value of 1,000 microfarads, your real-world measurement might pop up as something like 946 microfarads, or a 33 microfarad label might read as 36. This is totally normal. Due to manufacturing tolerances, the real-world measurement is going to be close to the label, but it is almost never perfectly exact. And wow, that brings us to the end of our explainer today. We've gone from microscopic electron standoffs all the way up to massive skyscraper power banks. So take a second and just look around the room you're sitting in right now. Which devices, maybe it's your ceiling fan, your computer charger, or your AC unit outside, are quietly relying on these invisible standoffs right this very second to make your modern life possible? It's pretty mind-blowing once you know what to look for, right? Thank you so much for joining me today, and hey, keep asking questions about the hidden engineering all around you. See you next time.